Now for general n, we can easily generalize our argument using our case for n equal to 1. So for general n greater than or equal to 1, we have that E is a finite union of boxes Bi, I from 1 to capital N, let's say, and each box Bi is of course a Cartesian product of intervals I1i cross I2i cross I3i and so on up to Ini. So there are n intervals because we are in dimension n, and each Bi is a Cartesian product of intervals. Now we consider the union of intervals I11, I12 and so on up to I1 capital N. So these are the first components. So the first intervals in B1, this is the first interval in B2, and this is the first interval in Bn in this Cartesian product decomposition. So now this is an elementary set. So let us call this set E1. So E1 is an elementary subset of R. E1 is an elementary subset of R, and by our previous proof for n equal to 1, this implies that E1 can be written as the disjoint union of intervals J1 k equal to 1 to n1, let's say. Okay, so where J1 k's are disjoint intervals. So we have already seen that for n equal to 1 we have such a decomposition of any elementary set. So E1 is our elementary set here, and we take a finite union of disjoint intervals J1 k. So similarly we do this for Ej, which is the union of I, j, k equal to 1 to n, and this can be written again as a union of j k equal to 1 to nj. So the number of such intervals may depend on these subscripts j. So we have to n1 here and nj here. So now we have that E, which is a union of these boxes Bi, I equal to 1 to n, and each such box is a Cartesian product I1i, I2i, Ini. Now I am going to write this Cartesian product. Now note that for each I, the interval I1i, since it is a subset of our E1, so I1i, since I1i is a subset of E1, so I1i can be written as I1i intersection E1, but now this is E1 is our union J1k, k from 1 to n1, and so this is a union k from 1 to n1 I1i intersection J1k. Okay, and these are intervals again these are intersection of intervals, so they can be either empty or it can be a non-empty interval. In both cases it is an interval. Note that the empty set is an interval. From our conventions, is an interval since you can take the empty set as the set X in R such that A less than X less than A. So this is basically our open interval AA, which is an empty set. Therefore our empty set is also an interval by convention. So in this union we have all of them are intervals and they can be either empty or non-empty, but nevertheless this is a disjoint union. Because each these J1Ks are disjoint for varying K. So now this is a disjoint union. So we can write I1I as the union of K equal to 1 to N1. I'm going to write Lik to be this intersection I1. So L1Ik is the intersection I1I and J1K, and these are all disjoint intervals. In R. So for each I we have this decomposition of each interval I1I as a union of disjoint intervals. Now our expression for E is union of Bi I equal to 1 to N, which is I equal to 1 to N I1I cross I2I up to INI, and we have that because of the decomposition of I1I and so on, we have L1IK, K from 1 to N1 cross union. So let me write here K1, K2 from 1 to N1. So we did this for the subscript, first subscript to 1. So for I1I we wrote here I1I as a union of L1IK, K from 1 to N1. So of course we can do this for varying first subscript as well. So I2I, I3I and so on we can write similarly, and that's what I'm going to do here. So now this will be a union from 1 to N2, L2I, K2 and so on. We have Kn 1 to N, L, N, I, Kn. So we have this decomposition here. Each of these L1IKs are disjoint for each coordinates. So now we have I equal to 1 to N union I K1 equal to 1 to N1 union K2 equal to 1 to N2 Kn equal to 1 to Nn L1IK cross L2I, sorry, this is K1, K2 up to Ln I, Kn, and now all these are disjoint. Therefore these are, if I denote this as B prime I, K1, K2, Kn, then this is a box and all these boxes are disjoint. So therefore we have expressed E as a disjoint union of boxes in Rn. So B prime I K1 K2 Kn K1 Kn I from 1 to, so I'm just going to leave it here. So each K1 ranges from 1 to N1, Kn ranges from 1 to Nn, and I ranges from 1 to N. So this is a collection of disjoint boxes. So we have expressed E as a collection of, as a union, finite union of disjoint boxes in Rn. So it's a little bit tedious, but the geometric intuition is clear, that we have to separate our coordinates, take the union, express the union of these intervals in each coordinate as a disjoint, as union of disjoint intervals, and then break each interval as a union of these disjoint intervals, and again take the Cartesian product. Now to come to the second point, we have to show that if E is a union, disjoint union, written in two ways, where BI's are disjoint, BI's, I from 1 to N, is a collection of disjoint boxes, in Rn, and so is this collection Bj prime I equal to j equal to 1 to M is also a collection of disjoint boxes in Rn. Then we have to show that the sum MBI I equal to 1 to N is equal to the sum MBJ prime j equal to 1 to M. Now one way to do this will be to get a collection of disjoint boxes which refine both these collections, which means that each BI's and BJ prime can be written as a finite union of even smaller disjoint boxes, and then we can use interchange of summations to prove this result. But I'm not going to use that way. I'm going to show that this MBI for each BI is a limit as n goes to infinity 1 over n to the power n, the cardinality of the set BI intersection z to the power d over n. So here z to the power d is simply the collection of integers d tuples of, sorry, this should be n, zn. So let me rewrite it. So k1, k2 up to kn, says that each ki belongs to z. So what we are doing here is taking, so let's see what it means for n equal to 1. So we have an interval I, so let I be an interval, and we have to show that the measure of I is equal to the limit as n goes to infinity 1 over n, simply n because n equal to 1, and the cardinality of the set I intersection z over n. First, our notation z over n is simply the set k by n. So n, capital N is fixed, says that k is an integer, and we are taking the cardinality of the integers of this rational numbers k over n, which fall in this interval I, and then we take a normalizing factor 1 over n and take the limit as n goes to infinity. So let us show that this is true. So suppose that I is given by the closed interval a, b. So we can do this same proof for if one of the endpoints is open or if both are open. But let's see for the case when both are closed. So then I intersection z over n, this is the set k over n, says that k belongs to z and this k over n belongs to I, which means that your k over n should lie between a and b, because k over capital N is an element of I, is a point in I, therefore it must lie between a and b. From this we get that NA is less than or equal to k is less than or equal to n times b. Now we have to take the cardinality of this set I intersection z over n. So we have to count how many integers satisfy this inequality. How many integers satisfy this inequality? So this is the number of integers between the points NA and NB. A moment's thought will give you the following formula. So the number of integers between A and B is given by the floor function NB, the ceiling function of NA plus 1. So we have the real line, let's say here is x, here is y, and we have to count the number of integer points that, let's call this A and B, or rather we have NA and NB. So NA lies between NA minus 1 and NA minus 1 and NA. So this is, please edit this part. So in our real line, let's say we have our point NA here and our point NB here. Then the floor of NA is the largest integer less than or equal to NA, and the ceiling is the smallest integer greater than or equal to NA, and similarly for NB. So here we have NB floor and NB ceiling. So we have to count the number of integers between the two. So since NB is in this point, the floor of NB is an integer, the ceiling of NA is an integer, so the number of integer points between these two must be floor minus ceiling plus 1. So for example, if this is 3 and this is 5, we will have another 0.4 here. So this is 5 minus 3 plus 1, which is 3 integer points in between, 3, 4 and 5. So we have this formula for the number of integers between which fall in the interval I. Now I have to take the limit as n goes to infinity 1 over n of this formula na plus 1, and I am going to show, I am claiming that this is simply is equal to b minus a. This is actually quite easy to show. So since the floor of NB is less than or equal to NB and the ceiling of NA is greater than or equal to NA, we have that NB minus ceiling of NA plus 1 is less than or equal to NB minus NA plus 1, which is simply n times B minus A plus 1. Therefore, if you divide by n throughout, you simply get B minus A plus 1 over n. Therefore, this term is less than or equal to B minus A plus 1 over n. Similarly, we have that NB, similarly, the floor of NB is greater than or equal to NB minus 1 and the ceiling of NA is less than or equal to NA plus 1. So this implies that NB minus floor of ceiling of NA plus 1 over n, this is greater than or equal to NB minus 1 minus NA plus 1 plus 1 over n. So if you compute this, you will simply get B minus A minus 1 over n. Therefore, we get that B minus A minus 1 over n is less than or equal to floor of NB minus ceiling of NA plus 1 over n, and this is less than or equal to B minus A plus 1 over n. So now take the limits on all three sides. This easily gives you that the limit as n goes to infinity, NB minus NA plus 1 by n, this is equal to B minus A, which is m of I. Now if you have a disjoint union, so let B be a disjoint union of intervals I equal to 1 to m. It's a disjoint union. Then the number of elements B intersection Z by n, 1 over n, this is the same as the sum of the cardinalities I intersection Z by n, I equal to 1 to m. So I can take the 1 over n inside, 1 to m, 1 over n dash I intersection Z by n. Now if you take the limit on both sides, so you can take the limit inside because you have a finite sum, so you get again 1 to m, m of I. Therefore, if you have a disjoint union for the case n equal to 1 in 1 dimensions, we have shown that this sum can be expressed entirely in terms of the union B, and therefore if two unions are the same, meaning that if B is equal to union I j prime, j from 1 to k, then also we have this sum, this sum ij prime j equal to 1 to k must also be equal to the same limit 1 over n b intersection z over n, and so these three things are equal, and so the sum of these mii's does not depend on the decomposition of B into various disjoint intervals. So we call this common value by definition as M of B. So one can easily generalize this same argument in n dimensions where you work coordinate wise and you will get the same answer. So I leave it that as an exercise, and we stop our lecture here. In the next lecture we will see some properties of this elementary measure which is defined using the sum of disjoint boxes.